Hey, Bill here. So in our last video, one of the things we did was to finish our arithmetic logic unit by assembling all of the pieces together. In this video, I'd like to explore a slightly different way we can assemble our arithmetic logic unit by combining all of the circuits into a single bit arithmetic logic unit. There are two reasons why we may want to do this. The first is to reduce the number of logic gates and the number of transistors used in our arithmetic logic unit. Second, it allows us to create a single component which, if we replicate it 8 times, can be used to assemble our final 8-bit arithmetic logic unit. So let's begin. First, let's start with our logic gates for addition and for subtraction. What's interesting about both of our addition and subtraction gates is that the logic for the sum output are both exactly the same, 2 exclusive OR gates wired in sequence. The only thing that differs between the two are the carry elements. Now, before I continue, a quick word about these 3 gates. In prior videos, we used 2 AND gates and an OR gate. What's interesting is that this pattern of AND and OR gates can be replaced with 3 NAND gates. If we iterate through all possible combinations of our 4 inputs A, B, C, and D, notice that the results are the same. This is because our output NAND gate below is on unless either input to the NAND gate is turned off. And since its inputs have been inverted, since we've replaced our input AND gates with input NAND gates, this means the resulting outputs is on only if either of the 2 inputs A and B or C and D are turned on at the same time. This is a general relationship between Boolean operations, but to me, it's easiest to see it if we show the Boolean circuits themselves. I'll understand if you want to rewatch the segment a few times to convince yourself. Now, the 2 circuits are basically the same except for one key difference. The circuit on the top takes 9 transistors to build. The circuit below takes 6. And when you're hand soldering transistors to a board, this is pretty important. Now, the fact that our 2 circuits share a number of exclusive OR circuits in common means we can save even more transistors. By merging our 2 circuits together, we can save up to 16 transistors since each exclusive OR gate requires 8 transistors to create. We can use this combination of selector circuits in order to choose which output we want to present to the output of our arithmetic logic unit. To do addition, you turn on the math and add control lines. To subtract, turn on the math and subtract control lines. We can continue to do this looking for places where we can piggyback on existing signals rather than create new gates. For example, here we see a NAND gate on A and B. Add a NOT gate, and we now have our AND operation with the addition of just 1 transistor instead of 3. We can find our exclusive OR operation here. That means we get our exclusive OR operation without adding any additional transistors. And notice something rather interesting. Rather than creating a separate OR gate, we get OR with our logic by enabling both AND and exclusive OR. As seen in our logic table, when we combine the outputs of AND and exclusive OR, we get OR. Our NOT circuit can be found here. This means we can add our NOT circuit without adding a new transistor. Left shift is easy. We simply route our carry value to our output and our input to the output carry signal. And right shift is only a little more complicated. We need to have a new input which allows us to get the carry value from the gate that is leftmost to take our carry signal rightwards and selection logic to handle this. The way this works is that when we wire up all of our 1-bit arithmetic logic units together, a leftward shift is easy. Our input carries to the next gate. Thus, as bits from our rightmost gates are entered, they're carried leftward by 1 position. Right shift, on the other hand, requires an additional input, our right carry input. By enabling our right carry input and writing them from left to right, as bits are entered from our leftmost gate, they're carried right by 1 position. And finally, we add our B copy operation. This allows us to copy the bus line into our accumulator without adding all that much additional logic. And that is the logic for our 1-bit accumulator. We can then use our gates to create a transistor circuit which can implement our logic. After drawing this circuit using Eagle, I went ahead and had this board fabricated. This board implements the entire logic of our 1-bit ALU. Now, assembly takes a few hours. Once it's fully assembled, we now have a single-bit arithmetic logic unit which can perform all of our basic operations. I've added a red and blue LED for debugging purposes, and because any computer built with transistors must have an array of LEDs, because LEDs are cool. Now, here we see addition. So I activate A, B, and carry. Here we see subtraction as I add A, then subtract B, then subtract carry. If A was 0, then this would be strictly a borrow. Here we see the AND operation, A, both A and B, only B, all off. By having A and exclusive OR on, we can see OR as A, B, only B, and both off, and exclusive OR with A and B, B only, and both off. And here we can see our NOT operation with A off and A on. And we can see how left shift and right shift works. With left shift, A goes to our carry, and carry goes to our output. And with right shift, A goes to our carry, but right carry goes to our output. Finally, we can see copying the B input with the B input on, the B input off. Now, of course, why stop with one board when we can assemble 8 of them? I've used wire wrap wire to connect these boards together. By plugging in 8 of these boards, we can now see our full 8-bit arithmetic logic unit in operation. These toggle units control the inputs A and B, and these toggle switches control which of our outputs we see. The red LEDs show our output lines, and the blue LEDs show the carry lines. Now if we enter 42 and 13, note that we turn on each of the switches to represent 1 and off to represent 0. You can see the LEDs show 55 here in the results, because this is 1, 2, 4, 8, 16, 32 plus 16 is 48, plus 4 is 52, 54, 55. We can show the results of subtraction by changing our control lines. Here we see that the results are 29. 1, 2, 4, 8, 16 and 8 is 24, and 4 is 28, plus 1 is 29. We can also iterate through the other Boolean logic operations. For example, we can show the results for AND. There's only one of the inputs that are on in common in our A and B inputs. We can show OR by combining and exclusive OR. We can show exclusive OR, and we can show the NOT operation. Notice that these LEDs are off where the inputs are on. And we can see the results of just copying the B input across our gates. And this is 13. 1, 2, 4, 8, and 4 is 12, plus 1 is 13. We can see how left shift works. Notice that the way our circuit is designed, the input A is reflected on our carry, and then the carry line is connected leftward, or in this case upward, showing the shift up one board. And we can see how right shift works. Again, A is reflected in our carry LEDs, but now the results are shifted to the right carry input, causing the results to be shifted rightward, or in this orientation, downward. And that's our complete arithmetic logic unit, built out of several hundred transistors and resistors. Of course, we are missing a few gates to determine if the results are zero, and for controlling how we handle carry from prior operations. But the point of this video is to show that there is nothing magical about integrated circuits. There is nothing magical going on inside an integrated circuit, such as the one that powers the heart of your desktop computer. This integrated circuit simply contains millions of these transistors, shrunk down into a very tiny little black box. But the principles behind what is going on inside this integrated circuit is no different than what we've shown here in a cube of transistors. And that's the point. That's the whole point of this entire series of videos. There is nothing magical going on inside. It's just a collection of transistors designed using the principles I've shown in these videos, with functionality that has been encapsulated into blocks we can understand repeated millions of times. And when you understand these principles, you too can understand what is going on inside of this little black box. Thank you for watching.